All right. So what I want to talk about in this lecture is Hooke's law. There's an E on the end there. I want to talk about which Hooke's law is the force of a spring is equal to K times delta X. And then I want to talk about how elastic potential energy, PE elastic, shows up in conservation of energy problems as 1/2 kx squared. Okay, so what we're dealing with here is something called K, right? And lowercase k is the spring constant. It is a characteristic of a spring. And what we're saying is when K is large, you have a stiff or strong spring. And when K is small, you have a weak or loose spring. Okay. Good. So the units on K are, oh, sorry, that's my coffee. Units are, of newtons per meter. And the way you can remember that, well, is a couple ways. You can take Hooke's law, which is sometimes written with a negative sign, and I'll try and show you that, and rearrange it, right? And get this. So then the units here are obviously newtons per meter. The way K shows up, or the way it's thought of, where it kind of comes from, is the idea that you can graph the force of a spring, units of newtons, versus the displacement of the object. Or I guess the displacement of the spring. Yeah, I guess you can think of that. Delta X is the displacement from equilibrium. And that's worth noting. But let's just go ahead and write this down right here. So what I'm trying to say here is that this is the displacement from equilibrium. And I guess if there was an object there, it would be of the object. So I can write that. I'm going to write of the spring or object. We'll just go with that. Okay. So K is the spring constant. And force spring is the restoring force. Always pointing, always, that's an exclamation point, always points towards equilibrium. Ooh, Equilibrium's hard to spell. All right, always points towards equilibrium. And K is always positive. So up here, if we make this graph, I'm gonna make it a few times here. Boom. Let's go with a different color. What the heck, let's go with purple. What we can see is that the slope, right? We think of just the formula or the proportional linear relationship y equals mx. We know that m is equal to y over x. So therefore the slope is equal to delta y over delta x, or we can say the slope is equal to the change in force spring over the change in displacement. Because that's kind of rough to write. Ugh, I don't like writing that. But you can see the idea here that if I rewrite this one more time, that the slope is going to be equal to force spring over delta x, right? That's kind of what I'm trying to say here, more simply, is that the slope is equal to force spring over delta x. And if this is true, then we can see this relationship right here, and then therefore the slope is k. That's my point. Okay, so since that's true, then we can see that this is a small k, this is a large k, because this is a small slope, and this is a large slope. So we can tell the spring constant, or the strength of the spring, from the slope of a graph that looks like this, of force spring versus delta x. Okay, good. And all right, so I think we're good there. Another way that this is written in the textbook, and it is like this. Let me rewrite this. And because I think on the AP test, this is the formula you get. I'm pretty sure on the formula sheet for Hooke's law. But you also see Hooke's law written like this in the textbook. All right, and this negative sign is helpful, but at the same time kind of problematic, because you're like, well, how can it be there sometimes and not there other times? What the negative sign tells you is that the force spring is restoring. So for instance, if you take, let's say you take a mass and attach it to a spring. All right, this is the floor, this is the wall. And then you take that mass and you compress it. You compress the mass, so this is now the spring. right? And you compress it by, this much. This is your delta x. And this is your old equilibrium. Right? This is equilibrium. So this is just rest, right? This is where this is resting right here. Okay, so you compress it, right? You push against it with your hand or whatever. This is your hand pushing against the mass. And when you do this, delta x points to the right. So delta x is positive, right? The mass and the spring displaced to the right. If that's the case, then we can see force spring is equal to negative k delta x. And if delta x is positive, we can do the math here and see that force spring then is negative k delta. I guess I'll keep writing it like that. We can see that force spring then is positive. Whoops, shoot. Dang it. I wanted my highlighter. So negative sign, force spring is negative, right? Because delta x is positive, force spring points to the left. And what that's saying is that the force on the mass, right, from the spring is going to be to the left. Because remember, the force of the spring wants to always point towards equilibrium, and the mass is to the right of equilibrium, so the force spring wants to point back to the left. All right, let's look at another example. What if you did the opposite, right? What if you took that that same mass? Let me see if I can extend my equilibrium line down. All right. And stretched it. Okay. Now we can see that this is delta x. And yeah, I guess I don't need to draw any more there. But now delta x is left, right? So it's negative. Okay, so and we said that force spring wants to point towards equilibrium and now points right. Okay, so what we're seeing here then is that our equation, dang you, why does it keep switching to the eraser? All right, our equation, force spring is equal to negative k delta x. That now this negative sign helps account for that, right? Check it out, right? This is going to be negative. So I'm going to go ahead and put that negative sign right here. And a negative times another negative is going to be a positive. See that? And which way is our spring point, right? We just said a second ago, it points to the right. It's positive. And so in the equation, this is positive. Whoops, I should be pointing that arrow over. Let me rewrite that. Force spring is positive or right. So what the negative sign gets at, right, when we write Hooke's law with a negative sign as force spring equals negative kx, is it gets at the idea, right, and I go back up here to where I did this, that that force spring is restoring, and it helps us account for that, right? It gives us a sign for delta x and then allows us to see that in a mathematical representation. But on the AP test, I think on the formula sheet, they just give you force spring equals k delta x, and you just have to realize that it always points towards equilibrium. Force spring does. All right, so there we have it. Let's go ahead and, is there anything else I wanted to mention? I guess something I want to mention real quick is that this is a proportional relationship. A proportional line is a linear line, which a linear line is a straight line with a constant slope. When you have a linear line, it can be proportional or non-proportional. Non-proportional means that it does not go through the origin. For instance, here is a non-proportional linear line right here, right? Where B is equal to this point right here, whatever the y-intercept is there. For a linear proportional line, whoa, there goes our axis. B is equal to 0, meaning that the line has to go through the origin. So straight line through the origin is proportional. Probably write that down. Maybe by straight line I just mean constant slope. And when we have this proportional relationship, what we're saying is we're saying that y is equal to mx. This is a proportional relationship. You can think of this being the same as y equals cx, and c is the proportionality constant. So things that have this proportional relationship, y equals cx, also can be written in the form of y equals mx, because we know that b is equal to 0, right? Y-intercept, I can't write y-intercept. Let me try that again. Is the origin. Right, that's what we're saying there. My point is that you can, when you have that y equals mx, you can make the graph, right, that we made a second ago with y being here, x being here, and the slope is meaningful, right? That the slope is or can be and that's what we saw a second ago, right? Where the slope is equal to k, right? When f of y, or y is the forced spring, and x equals delta x, or the displacement. We saw that the slope was equal to k. And I realize slope is change, but when we do slope, you always grab 2 points. But I guess you can get away with just grabbing 1 point here, because the second point could always be the origin, which is 0, 0. I didn't think about that. All right. So long story short, the reason I'm bringing this up is because for a proportional relationship, if you double force spring, then you double delta x, right? And this is what's so important about a proportional relationship. Or if you, because the slope is constant, because m is constant. So I could have said if you triple, or I could have said if you have, or if you quarter, right? And all these would be true. Then you triple, halve, quarter the other, right? So if we come up here, what I'm saying is if you double this, then you double this, right? And so that's super important here because K is going to be constant. The slope is going to be constant. The spring constant is going to be constant. You can't change the spring constant of a spring easily, right? It's a characteristic of the spring like mass. So that makes sense. All right, so we're going to rely on that. For instance, in this next problem, let's do an example problem here, or a few examples. This is stop to think. And in case you're wondering, this is all covered on page 233 of your night textbook. So this is Stop to Think 8.4. All right, and in Stop to Think 8.4, what they say is the end of a spring is pulled to the right by 4 centimeters. The restoring force is 8 newtons to the left. So let's draw that. So we have a wall, we'll say, a spring attached, and oh, geez. Let's do a dotted line. Let's do that orange dotted line. That was working really well. All right, so this is equilibrium. So this spring is just resting, right? And then we're gonna grab the spring, and we're gonna pull the spring to the right and displace it. Let's see here. From equilibrium, I'll just extend that down. The spring is displaced. This delta x, and that is to the right by 4 centimeters. Okay, so we pull it to the right 4 centimeters. The restoring force, right, of the end of the spring, I'm not sure what happened there. The restoring force, if this is delta x equals 4 centimeters right, then the restoring force always points towards equilibrium and is going to point left. I'm not sure why that's not exactly on the dot, but okay. And this is going to equal 8 newtons left. If you want to put a negative sign on there, you can, but I put left instead, and that works. All right. If the spring is returned to equilibrium and then pushed to the left by 2 centimeters, okay, so we're going to then return it back. Let's draw equilibrium again. Let's go ahead and now we're going to compress the spring half the distance, right? I'm trying to draw it the same as I did up there. This is not working out well with my drawings. All right, it's compressed. Check that out. All right, and we're going to say this is left. And if that's the case, then we know that the end of the spring is going to have a force pointed to the right because it wants to point towards equilibrium. Dang it, where's my... Okay. And I'm actually going to draw this again. Let me get one more chance at that. I'm going to draw it smaller. Okay. So we want to know what this force spring is. And because it's proportional, right, if we have the distance, right, we first stretched to the right by 4 centimeters, but now we're going to compress to the left by half. And if you half delta x, you half force spring. So this is going to be half the force spring, but pointed to the right. Oh, geez. 4 newtons. All right. So this lecture is going too long. This is going to be 4 newtons to the right. And so you get the idea here, right? Now, another way you could have solved this, if you didn't like to conceptually solve it, you could have been like, well, you could have been you could have said, well, Hooke's law, force spring is equal to K delta x. And you could have said that up here. Force spring is equal to K delta x. And you could have been like here and been like, all right, I'm not going to use signs because it's a restoring force. I'm not going to worry about the negative signs and whatnot. I'm just going to go ahead and plug in 8 newtons is equal to K delta x 4 centimeters. Probably get that into meters. That's kind of it's a problem. So that's going to be 0.04 meters. Then K is equal to what? K equals 8 newtons over 0.04 meters. That's going to be a large number. K is going to equal, let me get my calculator. 8 divided by 0.04 is equal to 200 newtons per meter. That's reasonable for a K value. Of course, the springs I have in my lab are, I think, in between like 25 and 100 newtons per meter. So this is a pretty strong spring compared to the ones I've had in the lab. All right. So what I'm saying here is K is characteristic of the spring. We could then take that down here and be like, oh, well, this time the force spring is 4 newtons. K is still 200 newtons per meter. What is the new delta X? We didn't know force spring. So what is the new force spring if delta X is halved to 2? Right? I think that's what we're saying, but we can't use centimeters, so it's going to be 0.02, 0.02 meters. All right, so what's 0.02 times 200? That's 4. All right, so what you see there is that we were able to shortcut all of that just based on the fact that we knew that the relationship between force spring and delta X is proportional, and that if you pulled 4 to the right and got 8 newtons, and then you decided to pull 2 or half as much, then you got half as many newtons, which was 4. The alternative way I showed you, which was to solve for the spring constant K, and then go ahead and plug it into Hooke's law and get the new force spring. Both ways worked. One way was much more conceptual. One way was much more mathematical. Both are good, but conceptual is the harder way usually, and a little more. It just helps to really understand what you're doing. Okay, so let's go ahead and move to this is on page 234. Probably gonna run out of paper here at some point. This is example 8.6. And it's something about weighing a fish. Okay. So it says a scale used to weigh fish consists of a spring hung from a support. Okay, so I think what we're going to do here is we're going to have a spring hanging from a support. Here's my support. Here's my spring. And then we are going to attach a fish. And, I got to draw a fish. Oh, dang. That's bad. Okay, something like that, right? Just looks really awful. Okay, whatever. All right. And it's weighing this fish. And it says the spring's equilibrium length is 10 centimeters. Boom. 10 centimeters. Once again, we kind of hate centimeters. So should we just get it? We'll do it in a second. We'll worry about it in a second. When a 4 kilogram fish, all right, I'm just going to write a 4 kg on this fish, is suspended from the end of the spring, it stretches to a length of 12.4 centimeters. All right, this is important right here, that this new length, I guess I'll just show you that, is 12.4 centimeters. But we don't care about the length of the spring usually, right? When we use our equations, even though that's what the question might ask us later. What we care about is the change, right, in the length from equilibrium. This is our delta x, or in this case, I'm going to use delta y since it's vertical, but you get the idea. Delta y in Hooke's law. And the first question says, what is the spring constant for this fish? All right, so what we're seeing here is the spring has an equilibrium, right? It's just going to rest right there. But there's two forces acting on this fish when it gets to this new equilibrium, right? And what are the two forces? Well, let's draw a dot on the fish. I'll draw it right there. What are the two forces acting on the fish? Let's see if you know this. All right, give it a try. Think about it. Two forces. All right, see how you did. First one, points down, gravity. Second one, points up. Let's go with orange. What's this going to equal? This would be the force of the spring, right? The restoring force, which points back towards equilibrium. Where's equilibrium? Right there, that orange dotted line, right? And so this is the force of the spring. Since the displacement delta y was in the negative direction and or down, then this restoring force is going to point up. I got to redraw that red because this delta y is all the way to equilibrium. Okay, so anyhow, two forces on this fish. All right, well, let's call, when we do these free body diagrams, let's call up positive, down negative. Let's go ahead and sum our forces. We know it's in equilibrium, so sigma Fy is going to equal 0. Force spring is a upwards force, so I'm going to go ahead and make it positive. Once again, I'm not worrying about the negative on the kx, right? The negative sign is going to be taken care of right here in this formula where I'm putting a positive sign on force spring, and I'm going to put a negative sign on force gravity, set it equal to 0. Force spring is equal to then kx, or k delta x. I got to be careful with that. Minus mg. All right, and we want to know what k is, so kick mg over to the other side, get mg, divide by delta x. We get k equals mg over delta x. We can then plug in, we said we were going to use delta y, whoops, but that's okay. I'll just make a correction there. Let me just write that in red. This is delta y, this is delta y. Okay, let's plug in some numbers here then. K is equal to the mass of the fish, which was 4 kilograms, times 9.81 meters per second squared, divided by delta x, which was, did we ever figure that out? No, we didn't. It's 2.4 centimeters, right? 12.4 minus 10. So 2.4 centimeters. We hate centimeters, so that's going to equal 0.024 meters. All right. 0.024 meters. If you want to put the 0 out front as a placeholder or just there, you can. All right, 0.024 meters. Let's do the math here. It seems like we're gonna get a large K. Let's see what we get. Wow, 1,635 newtons. This is quite the, what are my units? See, remember? Newtons per meter, right? This is quite the scale, quite the spring, quite the spring scale. All right, so there's our answer right there for K. And that's the answer to part A. In part B, they ask us, if an 8 kilogram fish is suspended from the spring, what will the length of the spring be? Okay, so check it out, right? We can answer this conceptually and we can answer it mathematically. So we're going to take the same spring, which has this K value, we know. It doesn't change based on whatever fish you put on there. The K is a characteristic of the spring. But since delta x or delta y is proportional to force spring, if we stick a 8 kilogram fish on there, then force gravity is twice as large because Fg is mg, right? So if we double m, we double force gravity. And if we double force gravity, we double the force spring. So if the force spring is twice as large, then what happens to delta y? Force spring is twice as large. Delta y is twice as large. So we know the answer here for part B is going to be, we said that was 2.4, yeah. So it's going to be 4.8 centimeters. Or we can say, or 0.048 meters is our new, this is the delta Y for an 8 kilogram fish. And if you're skeptical, right, and you're like, oh, let me see the math. All right, that's fine. So we would just say force spring is equal to K delta Y. Once again, we're not worrying about the negative signs because that just indicates a restoring force. So we want to know, or we know this new force spring is equal to mg, right? And we know that K is equal to that 1635. Is that what it was? I think it was what it was, yeah. Newtons per meter. Delta Y is what we want to know. We now know we have an 8 kilogram fish. So this is 8. And this is, of course, 9.81. So what I'm saying then is delta Y is equal to 8 kilograms times 9.81 meters per second squared. That's going to give us newtons on top, divided by 1635 newtons per meter. Newtons are going to cancel, right? kg meters per second squared is a newton. Cancel the other newtons. Meters floats to the top because you multiply by the reciprocal of a fraction on bottom. This is a fraction on bottom. So meters ends up floating up to the top. And we end up getting 8 times 9.81 is 78.48 divided by 1635, which is 0.048. 0.048 meters. And is that what we predicted? I think it was. Yeah. All right. So you can back it up with the math there if you want to. All right, good. Let's look at one more example here, and then we'll look at an energy example. This is example 8.7, and this is on the same page, which is 234. I like this example. I thought it was cool. You take a mass, 2.0 kilogram mass, you attach it to a toy train. Ugh. This is a train. Oh, geez. What the heck? What in the heck? All right, something like this. Okay. That's pretty good, except for the mass is floating in the air. All right, so something like that. All right, so we're going to then, this train's going to have a velocity. Let's use green. And it's going to equal, it's going to point like this. And it's going to be V is equal to 5 centimeters per second, which is 0.05 meters per second. Okay. And what you're going to do is or what's going to happen here is this train is just going to start pulling on this mass. Now, this mass has a static friction mu value, right? That is going to change, right? The mu static is going to start off small because the force is going to be small. But as the spring gets larger and larger, and as the train gets farther away and keeps pulling, we know the force of the spring gets larger and larger. So it's going to get so large that it's going to get to a point where mu static hits a mu static max. And we know that this is, I think it's 0.6. They tell us, yeah, 0.60. All right, so it's the coefficient of static friction, doesn't have units, and it's going to hit this 0.60, and then it's the mass is going to start to move, right? That's as much frictional force as you're going to get. So what I'm saying is, if we draw a free body diagram here, this static friction max should I write max there? I can. I don't know. I'm gonna write it. Okay. Is going to be at its maximum, right? That's as much as it can do. And at this point, the mass is going to begin to move. The force spring is going to be completely balanced when the object just begins to move. And so this is what we have happening, right? Because remember that as the delta x value of the spring gets larger and larger, that the force spring is going to get larger and larger too, right? And and that's going to be on this mass. So as this train moves right, the spring tries to pull the train left, but we care about the mass, and therefore the force spring on the mass is going to pull right, and those are going to be Newton's third law of pairs, the force spring on the train and the force spring on the mass. Okay. All right. Equal and opposite on different objects. Okay. So I think that works. All right. So let's go ahead and let's solve for this. So we want to know, when does the block slip? So when does this happen? So we want to know time. That's kind of interesting, right? So, okay, so, all right, let's do it the same way. Let's look at this in the x direction. Let's sum our forces in the x direction. And we know it's going to equal 0, right? This is the point where the force spring overtakes force friction static max. So we're saying then force spring is going to point right, so I'll make it positive, and force friction static max is going to point left, so I'll make that negative, set it equal to 0. Force spring is equal to, once again, I'm not going to put the negative sign on because I already applied a sign here with the positive sign because it points to the right. So I'm going to call it K delta X. Force friction static max is equal to mu static max, right? Which got larger and larger up to a point, right? This is like you pushing on a table. You can push with a tiny force, and static friction max is tiny. If you can push with a larger force, it still doesn't move, and mu static gets larger. But then if you get to a point where the force is the static friction is at its maximum mu, then the table will just start to move, or the chair, or whatever you're pushing on. All right, so we can say this is equal to mu times Fn. Oh, what's Fn? Let's go back up and look at that. And we want to know delta x, because we can use the velocity to find time. So what I'm saying is, we have a constant velocity up here. So we know v equals delta x over t, and we can say then that t is equal to delta x over v. So I'm saying we can use that to find the time, right? Because we know this can be our v value if we have delta x for this non-accelerated motion of this train, right? That how long it takes the train to reach this delta x value, which we can get from here. So I'm saying then that delta x, let me rewrite this. kick mu static max force normal to the other side. Divide both sides by k is equal to that. All right, so what the heck is force normal? Well, force normal, I didn't draw it in here, but it's equal and opposite. Points this way. It's a reactionary force to force gravity. And since we're on a flat surface, force normal is just going to end up equal to force gravity. It doesn't always equal force gravity, but when you're on a flat surface, it does. Because the surface reacts completely all of force gravity. So we can say then some of the forces in the y direction in equal to 0, Fn, then it has to equal Fg. So Fg is always mg. So we can say then that this Fn is Fg, which is equal to mg. So let's go ahead and sub that in and rewrite here. And I think with all of that, we can go ahead and solve. I think it was 0.60. Yeah, okay. Mass, did they give us a mass? They had to. It's a 2 kilogram block. I already forgot. I wrote that down up there, I think. Didn't I? Yeah. All right, G is 9.81. Notice this is all about the mass. We don't care about the mass of the train. This is the mass of the block. K is equal to, what did they give us a K? Ooh. Did they tell us? Yes. They said K is 50 newtons per meter. I should probably wrote all this down ahead of time. It's more reasonable. That's like the springs I have in the lab. Well, it's more reasonable for my lab. You know, obviously I'm not going to give you guys super strong springs in the lab and just hurt yourselves. That'd be bad news. And those springs in the lab are already strong enough. All right, so we can just go ahead and plug all this in and crunch this and solve. So 0.06 or 0.6. Yeah, I keep saying 0.6 times 2 times 9.81. Whoops. Divided by 50 is equal to 0.235 meters, which is 23.5 centimeters. I'm just going to write that down just so you can think about it logically. So it's totally reasonable, right? That's like a quarter of a meter stick. All right, so what is that time though, right? That's what we wanted to know. Time is equal to delta x over vx, and vx is constant, so this is fine. We don't have to worry about a k2 with an acceleration. This is what k2 simplifies to when ax is equal to 0. All right, so delta x is 0.235 meters divided by Vx, which was 5 centimeters per second, right? So 0.05 meters per second. Cancel off your meters. Seconds floats up to the top because you're multiplying by the reciprocal. And you end up getting what here? I think this is 4.7. Better check. 0.235 divided by 0.05. 4.7, okay. Units are seconds, which is a reasonable answer, 4.7 seconds. Okay, all right, there it is. And that's it. So hopefully that example helped, and a little review there of forces never hurts. Good, let's do a couple energy problems and we'll call it good. So for these, I'm gonna go to page, we'll go back to chapter 10. This is going to be page 313. We'll do numbers 33. I don't know how I'm doing on time. I'm probably going too long, but that's okay. 33, and it's worth it. 33 and 34. 33 says, A 10 kilogram runaway grocery cart. Oh, cool. Runs into a spring. Let's draw this. Yeah. All right, it's got the spring here. Runaway. All right, so it's got some initial velocity, which we want to know. That's what the question is asking. It hits the spring, and then this is kind of like the before, right? Then it's going to hit the spring. Let's draw the spring a little larger. And then it's going to stop. So, whoops, probably draw this a little closer to the wall. Okay. So it compresses the spring and stops. So VF is 0. And this is the after. All right, so this is a wall. So what we have here then is an energy balance, right? Where we have two types of energy happening, initial and final. And this is where we're going to see that the energy, the PE of a spring or PE elastic or U spring or U elastic, right? Whatever you want to call it. I think U is potential energy, the capital U. That this is all going to equal 1/2 kx squared, where once again, you should probably look at this real quick. This is the potential energy of a spring. This is the spring constant. And this is the distance, so we don't put a sign on it, stretched or compressed from equilibrium. Oh, that's hard to read. I'm sorry. So this is not the total length of the spring, right? This is how much it's changed. This is delta x. This is how much it's changed. But once again, we're not going to put a sign on it from equilibrium. And it doesn't matter. We're just getting squared anyways. But you get the idea. All right. So let's go ahead and solve this. EI equals EF. Or you could say MEI equals, you could say MEI equals MEF if you want, for mechanical energy, which is potential energy and kinetic energy. I'm gonna go ahead and write that. So we're saying that initially the cart was moving to the right, so the only kind of energy it had in the spring wasn't stretched is kinetic energy. It's no potential energy because it doesn't have a height in the from the ground. Final energy, it stopped moving, so its only kind of energy it has is spring energy. So we'll just say US, and we can go ahead then and solve for this initial velocity because we know that 1/2 mvi squared is equal to 1/2 kx squared. Okay, so let's start plugging in. Oh, halves can cancel. That's nice. I think we want to know what VI equals. So we can see here, let's see, VI squared is equal to kx squared over m, square root both sides, and we get rid of this. So let me rewrite that. So VI then is equal to the square root of kx squared over m. Sub in some values. I do not remember these. Apparently it is a 10 kilogram grocery cart. 2.2 pounds per kilogram, so 22 point, no, more than that. 20, what would that be? 23.2, no, 24.4. Oh, why can't I do that in my head? Oh, geez. It's just 22. Oh, okay. All right. Anyways, this is going on too long. K is equal to, they tell us 250 newtons per meter. And it's compressed by 60 centimeters, so 0.6 meters. This is a lot going on with the units here. Can we make sense of all that? I don't know. Yeah, so this meter right here is actually going to go to the bottom, because when you have a fraction on top of your fraction, the denominator of that small fraction just goes to the bottom of the big fraction. So these meters are going to cancel. So newtons divided by kilograms is what we have left. I don't like that. What did we forget? I feel like I forgot something there. Oh, this is squared. Ooh, almost forgot that square. So this is going to be square meters. So maybe I better slow down on these units here. And we'll deal with them in a second here. All right, so let's go ahead and simplify. Let's get a number here. So we're saying that 0.6 squared is just 0.36, right? It's going to get smaller. Yeah. So, all right. So we're saying 250. And 250 over 10 is just 25. So I can go ahead and simplify that to 25 times newtons per meter. And I told you that meter is going to actually go to the bottom, but I'll leave it right there. 0.36 meters squared over kg. Okay, that's kind of what we have here. 25 times 0.36. Let's look at units here. Let's see if we can make this a little bit easier to look at. This meters gets rid of this squared, because this actually gets to go beyond the bottom. So we're left with just a meters here on top. So we have Newton meters over kilograms. Let me multiply this first. 25 times 0.36 is 9. Okay. So we have, this is a nice answer here. So we have the square root of 9. Okay, but what about those units, right? We have Newton meters over kg. Well, a Newton divided by a kilogram is the same as a force divided by a mass. And that should ring a bell, right? Because A equals F over M. So we're going to have units of meters per second squared here, right? For our what I'm saying. So this is going to be 9 meters times meters over second squared, right? So there's our meters per second squared. So you're going to get meters squared over second squared, which when you square root that is just going to be meters per second, right? So we're going to end up getting 3 meters per second for our VI. All right. Okay, so there's our initial speed. The next one isn't much different. It's pretty much the same for 34. And they tell us a 15,000 kilogram jet lands on an aircraft carrier. Its tail hook snags a cable to slow it down. The cable is attached to a spring with a spring constant of 60,000 newtons per meter. If the spring stretches to 30 meters to stop the plane, what was the plane's final speed? So once again, in this problem, you have a plane that only has kinetic energy initially. It's then going to be caught by a cable that is going to bring it to a stop. So its energy at the end is going to be potential energy of a spring. And so we're going to go ahead and solve for that initial velocity. the same as what we just did. And we know these numbers are a little bit more difficult to work with, but we like the way those halves cancel off. And we want to know what was the landing speed. So what was the speed when it began the landing, what is VI? So we can see that once again, VI is equal to square root of kx squared over m. And we know that, we know these values. Let's see. K is much larger. This is going to stop a plane or a jet. So this K value is crazy. It's 60,000 newtons per meter. X is going to be 30 meters. All right, 30 meter sticks. That's pretty crazy. Once again, that's got to get squared. And then the mass of the plane is 15,000 kilograms. So the units are going to do exactly what they did before. And the numbers, 30 times 30, what's that, 900, I think? 30 30s, yeah. Times 60,000 is going to equal 54 million, I think, on top. So we end up getting 54 million. This is going to equal, the units are going to be meters squared per second squared. We already know that. And on bottom, we're going to have 15,000. And this is all going to be square rooted. So we can say then divide that by 15,000 equals 3,600. And the square root of 3,600 is just going to be 60, right? 60 times 60, yeah. Okay, so we can say VI is equal to 60 meters per second, which 60 meters per second is, what's that, about 120 miles an hour, and then you got to add some. So if you double 60, so maybe 150 miles an hour. So it's pretty slow, I guess, for a jet. But yeah, so there you have it. All right, that's it. So I can write that down. Maybe 160, I don't know, somewhere around there. All right, that's it. Hopefully this is making sense, and you can see the relationship now of springs to energy, and you understand where the K and X come from in this energy formula, right? That potential energy of a spring is equal to 1/2 kx squared. You can understand a little bit more about it now because you understand Hooke's law. So that was kind of the idea of today's lecture. Anyways, have a good day, and I'll see you in class next time.